Okay, so just a reminder of the exam logistics. So the exam is from 10:30 to 12:30 on Tuesday, and it'll be in Gradescope. And there will be multiple choice questions. There will be fill-in questions that have to be an exact match. And then there will be open-ended questions. So we'll, if we have calculations with decimals, we'll be more specific about exactly how many decimal places to do so that that can be graded properly. And then don't forget that that Gradescope does not allow me to choose the length of space to give you for open-ended questions. So make sure that you don't let it fool you into thinking you're only supposed to say 1 or 2 sentences. Remember that the point of the exam is for you to demonstrate your knowledge to me. And so make sure that you fully demonstrate that knowledge. It is open book, open note. It is closed people, obviously, but you shouldn't, if you're relying on looking stuff up in the videos during the exam, then you will not be able to finish the exam. So I do highly recommend, especially in this course, because it's been all video based, to take notes on those videos so that you're not trying to do it either all from memory or all from looking stuff up in the videos. So make sure you have some sort of reference with you. And then you're not required to connect to this Zoom room during the exam. You just can go straight to Gradescope and start at 10:30 and finish at 12:30. Okay. Also a note about this review. This is really to refresh you on the topics covered. It is true that some of the exam questions will be like some of these questions, but there are also going to be exam questions that are not like these questions, because this is sort of just to try to refresh you, to get you studying, expose what maybe you've forgotten that we went over, and to try to encourage you to ask questions about things that you don't understand, but it is not necessarily representative of the exam. All right, so any logistics questions before we begin? All right, so the way this is going to go is that I'm going to launch, there's going to be a poll for each one. I don't know how these are going to interact. So we'll see. Oh, okay, good. We'll see if that works. Okay, so this is a true false question, so just answer A or B. Quantum computing is poised to replace classical computing within the next century. True or false? Excellent. So we'll start the next one. True or false, modern cryptography only works today because factoring takes so long compared to multiplication. All right, well, one person hasn't responded, but everyone else has. That is true. If this becomes not true, which is anticipated with quantum computing, then figuring out the encryption key will be computationally feasible, which means that we'll be able to decrypt stuff. Okay, which of the following is not expected to be accelerated through quantum computing? Yeah, I see people are a little less sure about this one. Both C and D have been answered. And so that's good that you guys realize that encryption and molecular simulations are two of the applications. One of the other applications is optimization, like the traveling salesman problem is considered optimization. So these three are the ones that are expected to be accelerated, and sorting is not. Okay. And feel free to ask questions. Like I said, part of the purpose of this is to not only refresh your memory, but to give you reasons to ask questions. Okay. What is the outcome of this circuit? Okay, so most of you have responded. There was a little bit of uncertainty there, so let's go over it. The answer is 1, 1. Oh, I see the ABCD didn't line up properly, but I think people figured out that that was D. Okay, so let's look at it. So you've got the 0, 1. 0 is the control, which means that nothing changes. So then we get 0, white, black here. And now the control is a 1, which means it flips the target. So now it's going to be a 1, 1. So we've got 2 black balls on the result. So any question about that one? Okay. So we do have those little 1-page references that are linked to the lectures on the website. And so I would recommend printing those out for yourself before the exam so that you can have them handy. Okay. All right, so what's the outcome of this one? Okay, great. It looks like everybody got that one. Yes, it is 0-1. Kate, are you answering or are you not answering?
I'm not answering.
Okay, good.
But I'm keeping my eyes on the chat for questions. If anything like is a common question, I'll interrupt, but most of it's just been like little questions here and there.
Oh, okay, yeah, I can't even see that. So thank you. I didn't realize people were asking questions. Okay. Okay, great. Looks like everyone got this one. So we will move on. Unless there are questions. And you can also interrupt me verbally if you want, but yeah, doing in the chat is great because Kate can do it in parallel. Okay, let's look at this one.
Diana, so there is a question in the chat whenever we get to this in the review. One of the students wants to talk a little bit more about phase kickback if possible.
Oh, okay, great.
Whenever we get to those questions.
Yeah. I don't have any specific questions. Oh, I have sort of one. Anyway, I might need to go back to bring up the original lecture slides because I didn't specifically put phase kickback questions in the review. Okay, great. Everyone answered this and everyone answered this correctly. So we'll skip this one. All right. All right, so not everybody agreed. So this is a pretty important one. Remember that you have to take the square and absolute value. So A is not incorrect. You're gonna wanna make sure you remember that for the exam. And we take the term in front of the 0, not the term in front of the 1. Okay, so any questions on that one? All right, great. Everybody's got that, so we're good to go on that one. Okay, so this may or may not have more than one answer. Are you allowed in these polls to do more than one answer? I actually don't know. Okay, that's fine. So go ahead and answer what's the Brockett notation for that state? All right, so for this one, it's important to remember again that in Brockett notation is the square root of the probability. It's not the probability itself. So it's not 3/4, 1/4. It's root 3/2 and 1/2. Oops, that green one didn't quite line up, but the answer was B. All right, so go ahead and this one. Let's just skip this one because it's all messed up. The formatting is all messed up. So this one actually has 2 answers. It is both just the 1 in the ket, or it's 0 with 0 in the ket plus 1 with 1 in the ket. So there are 2 answers to this one. But the formatting messed it up. Okay. So how about this one? Okay, so we're good to go on this one. It's B because it's 1/√2 and then it's a negative phase. All right, so this is actually an open-ended question. So there's no multiple choice for this. In what way is measuring the length of a piece of paper using a ruler not like a quantum measurement? And in what way is it like a quantum measurement? So think about it for a minute and then we can discuss it. All right, so in one way that it is similar is that it may not be 100% accurate. A ruler only has so much precision, and it is also true that quantum measurements do not measure precise state. Quantum measurements are even less precise, but you would be allowed to say that that it is similar because it's not 100% accurate. It is dissimilar in that that level of inaccuracy usually makes no difference. So when we measure with a ruler, we're accepting that inaccuracy and it's fine. Whereas in quantum, that level of inaccuracy makes it very difficult to do computation. And using the ruler doesn't change the piece of paper in any way, whereas measuring in quantum does. So any questions on that? All right. Let's not do this one. That one's a 1. Okay, this one. And it should be, the 0 is A, 1 is B, 1 root 2, 0 minus 1 is C, and then this one down here is D. All right, so all four possibilities have now been represented in the results. So this means this was a good question to review. The previous question, if you do blackball HH, you get blackball back because H is its own inverse. However, if we have a measurement in the middle, that measurement outcome is going to be either, even though it's in a superposition here, when we do the measurement outcome, it's going to become simply a black or a white ball again. And so the input to the second H gate is merely a black or a white ball. And so the output to the second H gate is going to be in superposition. If it was a black ball going in, it would have a negative phase. If it's a white ball going in, it has a positive phase. So we can't tell what the phase will be. We know it's in superposition, but it could be either positive or negative phase. So it is option D, which is going to be circled in the wrong way because those rectangles are not lining up with the text. Okay, so what does it mean to have the ket, a minus sign inside the ket? What state is that? Oops, sorry, I didn't relaunch. Here we go. Excellent. Everyone who has answered got it correct. It is the second one, because it is what you get when you do an H gate on a black ball. Okay. All right, so then what is I in the ket? All right, so we have a few different answers represented. So this is when it's useful to have a picture of the block sphere, because if you remember the block sphere, the 0 and the 1, 0's on the top, 1's on the bottom. And then within the flat in the middle, there are 2 axes. One axis is plus minus, and one axis is I negative I. And so those 2 axes are both at the 50-50 point for 0 and 1. And so we know that it's either A or B. And so the difference between I and negative I is the phase, plus I or negative I here. So it is A. Okay. All right, so now we'll practice putting individual bits into bracket notation of multiple bits. So what is bracket notation for the combination of these 3 bits? Oh yeah, and letter than A through D. Okay, great. Pretty much everybody has voted. All right, so there are some different answers, but maybe the A was because of the bad numbering here. When I switched these from Google Slides to PowerPoint, the formatting got messed up a little bit. Okay, so either C or D is correct, either one of these last 2. I prefer the last formatting because it makes it explicit that it's 1 over root 2, but actually the next to last one is also acceptable because they are equal probabilities of the 2. Okay, in what basis is this one expressed? Okay, so it looks like people are getting it. That is computational basis. All right, and then this one, what basis is this? Great. Looks like most people are getting that. Yeah, so that is Hadamard basis because I see the plus and the minus. And so this is expressed in terms of what's the likelihood of the phase being positive versus negative. Okay, so now if we're given something in computational basis and we want to express it instead in Hadamard basis, what is the answer to that? And I did some, yeah, great, everyone got it. Because you have to do it turns out that to go to Hadamard basis, you use the Hadamard gate. And so that would be B. Okay. All right, okay, we will do the phase kickback right after this slide. And unfortunately, the formatting got messed up. So this is a CZ gate, which you can't tell. It's a CZ gate. It's starting with 2 black balls. And what I want to know is the answer, what the result can be. So the first result is here, where it's 2 black balls with a negative phase on the first one. And then the second B would be 2 black balls with negative phase on the bottom one. And by the way, the top is control and the bottom is target. You can't read that, but that's what it says in my original slide. And then C would be sort of either or both, that either one could be the output. And then D is neither. So those are your 4 choices. Okay, great. Right, and so everybody seems to be getting this so far. So the answer is either or both, because, and this is where the visual representation breaks down, because with the visual representation, we would have assumed that it could only be choice B, but in the mathematics, it can be either one, and you just saw the answer to the next question. Okay, so so this would be a good time to talk about phase kickback, because phase kickback also uses this property that when you have a 2-qubit function, that the minus can happen, the phase can move around. So let me bring up the phase kickback. Phase kickback is in fact one of my favorite things about quantum computing. Okay, so I need to switch my sharing to show this one. Okay, so if we start with this in superposition and the bottom one has a negative phase and the bottom one is the target. So theoretically, that this means that the control should stay the same by the end and the target should be affected, okay? But we know, so we put this in our 2-qubit format. So these are the 4 states we have going into the CNOT, and we do this 4 times. So we put each pair through the CNOT, and we know that what's going to happen is that if the top ball is black, then that will change, that will toggle or not do a knot on the second ball. Whereas if the top ball is white, it will remain unchanged. So we can see that, and the phase gets carried through. So we have 2 of these still with negative phase. And we can see that the top ball never changes, right? Because it's the control. And then the bottom ball for the bottom 2 also doesn't change, because that's the control was white, which means the target doesn't change. But on the first 2, the control is black and the target swaps. So we can see that that's swapped. And so because for the same reason as that CZ gate, which is we actually do this with the mathematics. We try with the visual representation, we're actually still allowed to do this one. The CZ one doesn't make sense, but this one does. But what we do is we look at this and we say we have 4 combinations here. We have to ask ourselves, okay, if we split this back up, let's reorder it so that that it's in orders, 1 1 1 0 0 1 0 0. So then we would split this back up, right? Because it's a 50-50, it's equal probabilities of all of the combinations of 0 0 through 0 1. So we know that we have a 50-50 probability of measuring a 0 or 1 for each one. But the question is, which ones have the negative sign, which ones are negative phase. And the only way to solve that is to look at it and say, well, if we multiplied these out with the FOIL method, right, with the tensor product, what would we get if we have the negative sign in different places? So we know that there must be a negative sign on the bottom one because we got a negative when the bottom one was the only black ball. So we know that. And then on this next to top one, we know that it's negative also because the top black ball. So that means that it has to be a negative sign on both of them. And so if you look at the very start versus the very end, we notice that in this case, instead of the control staying the same and the target changing, in fact, from a phase perspective, it is the control that changed. So that is phase kickback. When you're using a CNOT with superposition, it seems like the control should never change, but actually that phase, whatever phase is in the target, will end up in the control, because if the phase had been positive in the target, then the control would have retained its positive phase, because with no negative phase, we wouldn't have any of these shenanigans with the phase. Okay, so was there a specific question about phase kickback, or does this answer it? I don't know who asked the question or what the question was.
So the question was just an overview of phase kickback, because it was just a question or, oh.
Yeah, so Joao, do you have a question?
Yeah, so I think it was mostly an overview. I just wanted to ask like another clarification question, if that's okay.
Yeah.
So you also mentioned the CZ gate. So is phase kickback just something that happens with the controlled gates with the negative phase property?
Well, so phase kickback in particular is this circuit right here with the CNOT, and it has to involve it does have to involve 2 bits, right? Because it's moving from one to the other. The CZ gate is a similar effect with the phase being able to move. So CZ is not the same effect, but it's a similar effect in that it teaches us that phase isn't tied to a single qubit. It can move between qubits when you have a multi-qubit system. And so it is this fact that once you put bits through gates together, then a relationship occurs. And so even if they're not strictly entangled, that phase can be on either one. Whereas this one, the phase can't be on either one. This was actually the phase is on both. Both of these qubits now have negative phase, definitely. But it's still, I call them phase shenanigans, because it's like the phase migrates a little bit in a way that mathematically makes complete sense, but sometimes intuitively, based on how we're taught the CNOT, it wouldn't make sense. Okay. Any other questions on the phase kickback? All right. So I'll go back to my other slideshow. Which is which one? There we go. Okay. Okay, so now hopefully you've all forgotten what the answer was to the next one. Okay, so I have a parallel circuit, and I want to know what matrix would I use to calculate the outputs of 2 bits coming in to this circuit. Okay, so there are 2 answers fighting it out, I see. So the answer is the left-hand one. So we take the NOT gate and we embed the identity gate into the spots in the NOT gate where there would be 1s. Okay, so that might be something you want to have in your notes. Even if you have one example, then that can remind you of the general approach to take. All right. Okay, so now we want to know what matrix describes this serial circuit, which is an H gate followed by a NOT gate. And by the way, that should be in matrix. Like I'm just putting the ones and zeros that are inside the matrix, but just imagine there are the little matrix bars on the left and right of the grid of numbers. All right, so I see again, fighting it out between the two reasonable answers. So the answer is, oops. Nope, that's not the answer. The answer is A, actually, not B. So for this one, what's important to remember, unless I calculated it wrong?
Yeah, the one that
should be A.
Circled is the correct answer.
Oh, this is the correct answer?
Yes.
Don't we do the NOT on the left and the Hadamard on the right when we calculate the matrix? Like, don't we swap the order?
Ah, yes. No, you're correct. You're correct. So it would be the.
Yeah, it should be this one. So that's the trick for this, is to remember that you when you see a sequence of gates, you would be tempted to put the matrices in the same sequence when you multiply them out, but it's actually opposite, because you when you have a vector, you put the matrix that you're operating to the left of the vector, and then the next one to the left of that. And so you actually put you do your calculations right to left instead of left to right. And so you have to swap the order. So you put the NOT gate on the left and the H gate on the right, and you perform a matrix multiplication. So that's going to be one also that's important to put in your notes, so that you don't, because we will have this one like this on there in order to trick you in exactly this way. Okay. Yep. Okay. Which of the following is not true about teleportation? Okay, so almost everybody got it. So the correct answer is C, because there's no, we don't use a quantum light channel for the, if you look at the latency, it's the thing that gets sent at the moment is a classical bit. And so it is not related to, so it wouldn't be related to a quantum, I just made up quantum light channel. That was a made up, totally made up thing. Okay. Yes or no question. Does the following truth table, so imagine that this truth table describes a gate. The question is, does the following truth table describe a reversible gate or not? So it's just yes or no. So yes is A and no is B. All right, great. So almost everybody got it. The way I figure this out is to see if all of the answers are unique. And I noticed that 100 is here twice, which means that if I had the output 100, I would not know whether I would reverse it back to 100 or back to 001. So this is not reversible. Okay, so now I have a truth table that is reversible, and I want to know what is the matrix for that truth table, or for that gate. And again, assume that the matrix bars are on the left or right. Okay, looks like I'm tricking everybody here. So everybody got my trick answer instead of the correct answer. So, okay, almost everybody. There's no D. D is blank. Somebody answered D. Okay, so let's look at how to do this. Again, the reason I put this is because it's very easy to mix it up. So the way the matrix works is that for a given row, that is determining the answer to that row in the answer, right? And so if and the position in the row determines which one of the original vector is going to be pulled and copied to be that. So this first row corresponds to the answer being 0, and the position in the row corresponds to which original item became the answer to 0. So I look here and I say, oh, 0, 0, 0 on the answer is drawn from 1, 1, 0 in the initial vector. And so that means that this B must be correct. Whereas this one is the other way around. This one is, oh, I have row 0, I'm going to put a 1 in position 1. I have row 1, I'll put a position in position 1, 0, 1. But that's actually the opposite way to go about it. So you need to go about it this way right here. Okay, then another question is, what is the matrix for a C swap? That would be a controlled swap. That would mean that if the control, which would be the top bit, is a 0, no change occurs. And if the control is a 1, then the 2 bits get swapped. Oh, sorry, I need to relaunch the poll. Okay, great. So my distractor is working. So a lot of you got the right answer, which is A. So with any controlled gate, the first half is identity, because that's when the control is 0. And then we look at the swap gate. And so we have to remember in a swap gate that 0, if you have a 0, 0 or a 1, 1, no change occurs. So the first and the last choice is still on the identity. We only swap if we have a 0, 1 or a 1, 0 on those middle bits. So we get A. So any questions on that one? Okay. Oh yeah, and we can see the truth table here. So if you're confused, when I was doing this one, I did a truth table just to make sure that I had it correct. And then you can very easily see that these are the only 2 that have differences between the input and output. So those are the only 2 that aren't going to be on the diagonal. Okay, so now I'm defining a new one, which is, I'm calling it a rotate right. So that means that if I start with A, B, C, D as all the terms, that what I'll end up with is that each term will go to the right one. So A will now be at 0, 0, 1, B will be at 0, 1, 0, and H, which is the 8th one, will be brought around to be the first one. So the question is, which of these is it going to be? All right, so it looks like the 2 reasonable ones are fighting it out. About equal number of people are choosing B versus D. So let's look at this again. You take the output and you see where it's grabbing from the input. So you see that 0, 0, 1, so row 1 is grabbing from index 0 of the input. So that means that row 1 must have a 1 in the 0 position. You can see that the output of 0 is drawn from the last one. So row 0 must have a 1 in the last position. Okay, so that means that D is the correct answer. Okay. Any questions on that? It seems like this was now the same one 2 times ago. It was the same issue about row versus column. So make sure that you're not mixing those up. You take the row of the answer and the column of the input. All right, so now go ahead, it'll take you a few minutes, but I want you to figure out the matrix for this circuit. So I don't know if people are still working on it or not many people have voted yet. So maybe I'll go over how we would solve it. So first we would figure out the matrix for these 3 bits in parallel, which would be using the tensor product with 2 identities and the H. So, and that's the same as this one. And then we would, in serial, we would put the 3 and multiply them all together. So it is D. Is that one that people want me to work out? Raise your hand if you want me to work that out for you. Yeah. Okay. So.
I have a quick question here.
Yeah.
So I did this one using the identity, and I just wanted to, like, is that a valid way to do it, or did I just, was that a coincidence?
In what sense you did it using the identity?
Like, I saw that the H naught and the H, I think, is the Z gate. So I did this as if it was like a Toffoli C gate or Z gate. And then I just have the -1 there in the lower right.
I see. That's interesting. I don't know if, I mean, that's not on our list of conversions and identities. It certainly worked. I guess it worked in this case. I don't know if that's
if it's like always true.
Right, because right. I mean, it's both true that if you have the H gate on either side of a naught, you can make it a Z. And also if it's on the either side of the C naught, you can make it a controlled Z gate. So yeah, I think you can, because the pattern of when you multiply everything out is going to be the same. So yeah, so I think that doing the identity does actually work.
Yeah, cool. Thank you.
And then that makes it much easier. So if you take these 3 and compress them into a Z, then you know that you have the identity, and then you just have the CZ gate at the end. So that's very interesting. But the other way to do it would be to take the 2 identities with the H and figure out the matrix for that, and then multiply those with the Toffoli gate. Okay. Were there other people who wanted me to go through the math of the individual steps? So raise your hand if you wanted me to go through the math of the individual steps. Okay, then we will move on. How are we? We're doing 32. Actually, we're making pretty good time. Okay, what is the purpose of end syllables? Okay, great. Everybody who's voted so far has gotten it. It is in fact B. It is to make an irreversible operation reversible. Okay, what is an EPR pair? Yeah, so I can see that, so C and D are very close to one another. And so it's a subtle difference. So EPR pairs are used for teleportation, in which you measure one, send over a bit, and use that to reconstruct the other one. But they aren't, it's not a copy. It's when you measure the one, you have to send that information over and it reconstructs it. So it's not the case that you have these 2 copies and you're measuring one and getting that information, but then the other one is still there. So C sounded like it could be, but it's a very important difference that it's not a copy of the qubit. At the very beginning, when they were first made, they were identical, but then there were operations performed on one of them, so they're no longer identical. So they are just an entangled pair of qubits. Okay, so what is the no cloning theorem? Great. You all got that? Oh, all that text is getting messed up. Well, I think you can do it just by the symbols. This is a circuit simplification problem. So I will give you some time to figure out the simplification for this one. All right, so some of you have finished. Most of you are getting it correct. It is this one right here. And so I can step through it for those of you who didn't have a chance to finish or didn't get it correct. So let's look at how it works. So we start with this circuit, and then we can expand the C naught in the between to flip it and put H gates on either side of it. And then we can, so then we take the H naught H and turn it into a Z, and the HZH and turn it into a naught, and then do the same thing on the right side. Okay. And then we're allowed to scoot these over, so we can trade places between the C naught and the Z and the naught. I mean, we could do them one at a time, but I just recognize that I can do both of them. And then these two are the same, so they go whoop, and they disappear because they are identities of themselves. And so we are left with the C naught that's just upside down compared to the original C naught. Okay, so now we're doing some with the representation of the block sphere. So we're going to do some simple calculations and figure out where it ends up on the block sphere. Okay, great. So I see two different answers coming out, B and D. So when we put the white ball through the knot, it becomes a black ball. And when we do an H gate on a black ball, that has that gives us the negative Hadamard state. And so it will be D. Okay, so any questions on that? All right. Okay, so now let's do the same thing, but let's add a Z gate here. Okay, so the Z gate flips the phase. And so we will go from negative phase to positive phase. So the answer is B. Okay. Now let's take this one. We have this as the input. So the input is the positive Hadamard state. And we want to see what happens when we put it through a NOT gate. Okay. Okay, so most of you are getting it correct. There will be no change because the NOT gate changes with respect to 0 versus 1, and we're already at 50-50 0 versus 1, so it will not have a change. We can also calculate that out with the matrices if intuitively it doesn't make sense. Okay. So I've drawn my red arrow is the state I'm talking about. And so what we want to figure out is what are the two angle measurements for the negative Hadamard state in this case. Oh, wait, I don't think the right answer is here. Wait a second.
I was about to say, I think one of the copied answers,
yeah,
the correct answer
was supposed to be the correct answer. So the correct answer is not here. Wait, no, that is not, and that is not the correct answer. I don't know what happened there. I don't know what I was thinking. Anyway, so it should be that here should be there.
I think that's the correct answer for pi over 2, because it's a half rotation. So pi would go from ket 0 to ket 1, and pi over 2 would leave it halfway, and then pi over 2 on the z rotation would bring it back around.
So on the first rotation, wouldn't that rotate it to the positive Hadamard? Right?
Yes, and then the phi rotation would bring it back to the, so if we have theta.
But one's 90 degrees and
pi.
one is 90 degrees and one's 180 degrees, right? You only have to go 90 degrees to get to the Hadamard positive, but you have to go 180 degrees to get from the positive to the negative. So it was supposed to be, this one. These two were I was supposed to be toggling. Oh, let's see how, I was supposed to be toggling. Anyway, I had some pattern here, but this answer was supposed to be there. I just messed up when I wrote it. I don't know if I didn't finish that one or what happened there. But this is what I intended to have. Okay, so let's see if I messed up on the next one. Yeah, because I apparently didn't finish these. Okay. Oh no, there was only one, so apparently I just didn't finish it. Okay, so what is the key to the Bernstein-Vazirani algorithm? What effect is it taking advantage of for quantum? Okay, so most of you have weighed in. It is phase kickback. Bernstein-Vazirani is the canonical example for phase kickback. It's the simplest example to show phase kickback. And then Archimedes, not surprisingly, is interference, which is why I chose those two algorithms as the first two algorithms to present, because they show those two effects. Okay, Grover's algorithm. The question is, what matrix could be used to flip the phase of a ket 110 that is chosen as the search object for Grover's search? All right, so most of you have weighed in, most of you got it right. It is C, because all of the bits need to stay unchanged except the one corresponding to row 110. So 110 is the next to last row, and the only change is changing the phase. So we have -1 there. Okay, another Grover's algorithm. What circuit could be used to flip the phase of ket 11 that is chosen as the search object for Grover's search? All right, so we have several answers that have come in, and we have lots of guesses. People guessed all of A, B, and C. So the correct one is A. Let's look at B. So B would say we're flipping the phase of the second bit. Okay, and so if both of them started as positive phase, then what that would mean is now I'm trying to think of what the intuition is for this. I mean, we could construct the matrix, and we would see that it would have two -1s in it, because we would be doing a parallel construction. And so we would be doing both we would be copying that Z matrix twice into it. The other way of looking at it is like if we thought of it as the visual representation, then we would be, if these were both, well, that would be if they were both in superposition. So anyway, this is the only one that has, if we look at the matrix, has a 1, 1, 1, negative 1. And so that's the one that is going to give us the correct answer. This Z1 also, if you do the parallel construction, if you multiply that out, it's not going to get you, you're going to be doing, you'll have 2 negative 1s in it as well, because you'll be having a Z gate copied in both the top left and the top right. And so with the bottom right one negated, so then there'll be 2 negative 1s in there. Okay, what is the greatest common factor of 33 and 57? Yeah, so everybody's getting it right. It is 3. Okay, what statements are correct about Shor's algorithm? And if more than one is correct, then just do either one. Okay, so we have lots of answers again. The 2 answers are that Shor's algorithm makes use of Euclid's algorithm, and that Shor's algorithm transforms a bad guess for an integer factor into a better guess. Okay, so we don't have time. We're at the end of time, so I'm just going to show the answers, and then you can go back later and look at these and work them out. Yeah, so the whole point of the N in NISC is that they're not error corrected, and so actually one thing about IBM's machine is that it's had lower and lower connectivity as time has gone by, and that might be part of where they're getting their volume gains in reliability.